Hey guys, I still miss you. So today we're going to start what is usually the last lesson I teach of the school year, but they are not going to be testing you over partial sums. Over parametrics or polar or even vectors. You will see vectors in physics though. Know that we are doing those units after the AP exam specifically because you were supposed to have seen most of that information in pre-cal. However, UT on-ramps does not cover them in such a way that prepares you for your college professors. I hope that that's clear why we are continuing and why I'm not just going to give you a fluff project at the end. Hopefully we'll have time for a fluff project. I really want to. So that's number one. Number two, I am supposed to give you 2 assessments per school board rules between now and the end of the school year. The end of the school year, if you are not aware, is May 26th. So those 2 assessments are going to be the musical, the questions for the musical, combined with the practice AP exam, both of which will be occurring this week. It is really important that you understand that your time is restricted on the practice AP exam, and you need to let me know if you have extended time and exactly how much extended time you have, because part of this practice AP exam will be learning how quickly you need to get these problems done. And that is going to be the biggest lesson you're going to learn from practicing this AP exam. So here we go. We are now in the Lagrange form of the remainder, also called the Lagrange error bound or Taylor's theorem remainder. The information that you see in front of you is by Paul Forrester. Oh, that's really messy, isn't it? Paul Forrester is a really super nice man who has now retired, but just recently he was still teaching at Alamo Heights High School in San Antonio up until about 2 or 3 years ago. He has several textbooks that are on the market. I choose not to use them simply because I feel like the language in the books that we use, the language is easier to understand. So Paul Forrester writes books that are super problem-based, super real life problem-based, and they're super wordy, as you can see in front of you. Like this is not even like the half of it that you would get on a page. They're great. They're word problem after word problem after word problem, but I'm more of a fan of meeting out or separating out just the math because I want to test you over your math skills rather than your English reading skills. Okay, so when we are talking about the Lagrange form of a remainder, there's a partial sum, which is the first few sums of series. The tail is the rest of the terms of the series after a partial sums, and the remainder is a number of things you get by adding all the terms in the tail. So f of x is always the partial sum plus the remainder. The error is the error you make by assuming f of x equals that partial sum. So the error is the same number as the remainder, and an error bound is known to be the greater than the absolute value of the remainder. So for an alternating series, the absolute value of the first term of the tail is an error bound. You already saw that at work. So in the integral test of convergence, the improper integral is an error bound. Now, Monsieur Lagrange is credited with showing that the Lagrange remainder is exactly equal to the first term of the tail, but with its derivative evaluated not at x equals c, but at some number z, which is between c and the value of x at which you are evaluating this function. As this value of z comes from repeated application of the mean value theorem, dun dun dun, mean value theorem, hey, we've heard of that. There is often no way of knowing exactly what z equals, but if you can find a number that is an upper bound for the derivative between c and x, then you can find a Lagrange error bound. So Taylor's theorem states all this junk below, which you've seen before. Sorry, my throat itches. That probably was a weird noise on the... And I think we talked about, I think I talked about this once and I said, but we'll talk about that later. And it feels like it was a month ago, but I think it was only like a week or two ago. So Taylor's theorem states that that remainder has to be less than or equal to this particular value right here, and that f to the n plus 1 of z is the maximum between x and c. This gives us a bound for the error. It does not give us the exact value of the error, and the bound is called Lagrange's form of the remainder, or the Lagrange error bound. So, let's see what I want to talk about here. At this point, you should be able to figure out not what this says, but what it's referring to here. So notice the notation. In the question from 2011, students were asked to demonstrate that the Taylor series at 1/4 minus the function's value at 1/4, the difference between the two of them is less than 1/3000. So, in order to do that, the students had to apply this Lagrange error bound and show that that value was less than 1/3000. So I want to emphasize that they are using this to prove, so we're back in proof, which you have seen very little of since geometry. You have seen some of it in calculus, but the key to this whole Lagrange thing is proof. Okay, so first we're going to look at this function below, and we're going to write the third degree polynomial for f about x equals 2. And here we go. We use our formula for a Taylor polynomial centered at 2. We go ahead and substitute the values for our function and its various derivatives. One place I thought you might get lost if I didn't point it out is that 2.3 minus 2 is 0.3, so that's how I jumped from this step to that step. So I was a little concerned that you might get a little lost. And then I substituted in that number and I got a value of 6.921, and that is approximate. And then we need to go ahead, and that you should be able to handle at this point. We're going to look at b. The fourth derivative of f satisfies the inequality that that particular derivative has to be less than or equal to 9 for all x in the closed interval 2 to 2.3. So we're going to use this information to find the error in the approximation of f of 2.3 found in part A. One thing that has always made me uncomfortable about this particular piece right in front of you is that they don't explicitly state that 9 is the maximum that the theorem refers to. So 9 is the absolute maximum that that fourth derivative and coefficient of the lobbed off term could possibly be. So we use that 9 as our maximum, and that is the maximum error in that approximation. So we are going to go ahead and figure out I almost said the actual error. We are going to figure out what our bounds are for the actual value of f of 2.3. In order to do that, we're going to take our approximation, which is right here, and we are going to add and subtract our error from that. I would like you to notice here that I did not round or truncate until I was completely done. That happens to be a personal preference of mine. That is not necessary, but you do need to remember that you need to be all the way out to the thousandth place no matter what. You can't round. You need to have at least 3 decimal places. I'm trying to say this as clearly as possible. So then we come down to our next question. I'm sorry, that was a little bit of a jarring transition, wasn't it? So could it possibly equal 6.922? Well, yes, it could be, because 6.922 is in that interval specified in C. Now, it cannot be 6.927 because that is larger than the upper bound. Okay, I want to make another note about both the AP exam and communicating with your professors. Do not use anything other than standard abbreviations. The BC that I use, that is actually shorthand. That is a standard abbreviation. If you were to abbreviate, say, upper bound and instead write UB, you might not get credit because that is a fanciful, imaginative, lovely, but unacceptable abbreviation. So, onwards and upwards. I don't know why I say that so much. It's dumb. Okay. Give me a second. I got to fix my screen because all I can see is the bottom right corner. The first thing we're going to do is we are going to use our function and its derivatives to calculate the values of that function and its derivatives at 0 so that we can set up our Taylor polynomial, which PS is a Maclaurin series. So here we go. I guess you could still call them Taylor polynomials though, because they're polynomials, not just straight series. Okay, here we go. And there we have all of our terms. Excuse all of the very strange boxes. I, for some reason, just completely wrote this as, I forgot all of the labels, so I had to rewrite it. So in any case, there we go. We have all of our coefficients for all of our terms, and now we just need to create our third degree polynomial. And there we have our Taylor polynomial without our fourth term. So you may have noticed that I went ahead and I found the fourth term. I found the fourth term very intentionally, or the fourth derivative. I found the fourth term and the fourth derivative very intentionally. I did that so that we could calculate our error in the next step. I tend to usually go one more decimal than we need to, one more derivative than we need to, just in case I need it later. I've always been like that for as long as I remember. So now we've used Lagrange error bound to show that the absolute value of f of 1/15th minus p of 1/15th is less than 1/1200th. So here we're trying to find the Lagrange error bound to show that the difference between the actual function value and the value of that Taylor polynomial at 1/15th, and the difference between the two of them, the absolute value of the difference between the two of them, is less than 1/1200th. Okay, so I did some finagling here, and I allowed myself to think about, I would not ordinarily write this, the decimal here, and I rewrote it as 4 over 10,000. And 4 over 10,000, granted, is a slightly different decimal, but it still gives us the opportunity to simplify that fraction and allows us to compare it in a more straightforward manner, 1/1200th. So when we compare it to 1/1200th, we see that it is in fact smaller, and this particular number up here is not significantly different enough from the fraction that we have simplified to, so we can continue to think about it this way. This thought process allows us to say that the difference between the function value and the Taylor polynomial value is in fact less than or equal to 1200. It is in fact less than or equal to, or less than 1 over 1200, but all the same. Okay, I am stopping this video now. I am going to, I was going to break this up into two, and I guess I can't because I already took the pictures. Poop. Okay, I want you to stop this video now. I want you to take a break. Please, go get some water, go hit some tennis balls, go to a driving green if there is such a thing in this environment. What else do I have? Go play your instrument. Who else do I have in class? Go draw. Do something. You need to take a break because this is going to be an exceptionally long video because I'm trying really hard to address all of the questions that I've had on this video in years past, because out of all the lessons, this particular day creates the most confusion in people's brains, and I get a lot of questions, and I'm trying really, really hard to be clear here. Take a break. I mean it. Go take a break. Turn it off. Come on. Okay, onward to the alternating series remainder. So if a series has terms that are alternating, decreasing in magnitude, and having a limit of 0, then the series converges so that it has a sum S. If the sum S is approximated by the nth partial sum S sub n, then the error in the approximation, the absolute value R sub n, which equals the sum of the series minus the nth partial sum, that will always be less than the absolute value of the first omitted or truncated term. So here we go. On this first example, we find all of the values for the derivatives that we need, and if you're me, which you are not, you go ahead and find the next derivative, Then you write out your series. Once you've written out your series, you use that information to go ahead and make a calculation. That rhymed. That was gross. I think I just said that we could find a value, but actually all we're looking for here is a second-degree Taylor polynomial for f about x equals 2. Then, in part B, we find the second-degree Taylor polynomial for x about x equals 2, which will approximate f of 2 with an error of less than 1/100th. Our approximation for f of 3 is 1/18th. Now we need to go back in and find s minus s sub n, or r sub n. So here we do our calculations and we discover that r sub 2, or s minus s sub 2, is less than the first or omitted or truncated term, which is 1 over 27 times 1 over 3 factorial times 3 minus 2, which simplifies to 1 over 162, which is definitely less than 1 over 100, or 1/100th. I don't know why I said it that way. So we definitely have an error less than 1/100th. So as you can see, the math is pretty simple. Now walking into the AP exam, or I don't know what logging into the AP exam, you need to remember the differences between alternating series remainder and Lagrange error bound. That's what's hard. These little tiny pieces aren't hard. Keeping them all straight is difficult. Okay, we go ahead and find the third degree Taylor polynomial about x equals 2 for the function f. Once we've done that, we need to find an estimate of the value f of 2.8. So once you've estimated the value of f of 2.8, you need to go ahead and show that your remainder of the r sub 3 is less than 1.8, which is being referred to right here. Okay, sorry, I'm having trouble keeping track of what I'm doing because I'm doing too many things. I'm listening to old folk music that brings back memories from my childhood. At the same time, my sister's texting me, and then I'm trying to teach you all at once. Okay, you don't really need to know all that. You don't really care. Okay, so we look at this graph, and we see that between 2 and 3, the maximum there is 7. So that gives us our upper bound on our series remainder. Excuse me, something's happening inside my throat. So that is, let's see if I can remember where it is referenced on the page. I think it's on a previous page. So that is the absolute maximum that your remainder could be. So, or your derivative could be. So, I don't know why I said remainder. I don't know, guys. I'm sorry. Okay, here we go. Trying to focus. Let me, now this is one of my favorite songs everywhere. Anytime. I gotta pause it. It's Blowing in the Wind. I love that song. Okay. That's why I don't listen to wordsy music. 3 is less than your fourth derivative. Because that up there, the graph that's on this page, that is the graph of your fourth derivative, in case you forgot or in case you didn't notice before now. So your remainder or the absolute value of your remainder, is less than 7 times 2.8 minus 2 all to the fourth divided by 4 factorial, and that remainder, or the absolute value of that remainder, is less than, when you simplify that. Okay, so we go ahead and calculate out the upper bound of that remainder, and we get, when we put it in fraction form, 224 over 1875. If you don't like that in fraction form, haha, you're doing too much work. Or you can say that it's less than 0.119 is less than, what is 1/8 as a decimal? Who can answer that question? Robert. Oh yes, you are correct. Use your calculator and you get 0.125. Beautiful. Okay, so to recap everything that's going on this week, first of all, there's going to be Calculus the Musical. You will need to access that and answer questions of that. It does cost $5. If you cannot pay for it, you need to let me know, because I do have somebody that can help you pay for it and lower that cost to $2. But I don't think $5 is any big deal. I'm sorry. I personally don't think $5 is any big deal. But if it's a big deal to you, you need to let me know. Because we can get it down to $2, and we might even be able to get it down lower. I don't know. So you need to watch Calculus the Musical, and we need to figure out a time when you can take the Practice AP exam. Make sure you go over the rules for the Practice AP exam, because there are time limits. You need to make sure that you go over what is involved in taking the Practice AP exam. You need to comb through the AP website and make sure you go over the rules. I cannot emphasize this enough. You will have 25 minutes to do the first question and 5 minutes to upload your answers. No more. Once you have done that, you will have a limited amount of time to do the second question and upload your answers. If you have extended time at all, now is the time to speak up. I need to know now, so that when you take the test during the week this week, whenever you choose to take it, you need to make sure that I know what your extended time is, so that I set the timer appropriately for you. Understood? Capiche? Okay. Okie dokie. I miss you terribly. I really wish we were all in person. I miss the days when I would teach this lesson and everybody in the room would be looking at me like, oh my gosh, just let's get this over with. I'm so sick of Miss Marty. I'm so sick of school. And right now, we are all missing school, and this is terrible. But in the meantime, you get to hear me talking about my weird music. So sometime I will introduce you to my weird music, because my tastes are all over the map. When I was in high school, I was a punker. So there you go. There's a little tidbit for you. Y'all have so much fun. Try really hard to take care of yourselves. Enjoy the video of the two gals. I don't know where they were. I think it was Spain. They play tennis on the rooftops of buildings. It's really impressive because they're quarantined and they're playing tennis from building to building. Really impressive. Y'all take care. Pet your animals. Hug your family. Eat your greens. Take care. Bye-bye.